Okay, so why don't we go ahead and get started? I want to welcome you to our first statistics seminar of the fall. My name is Paul Kolm, Associate Director at CBIDS at MedStar Health Research Institute. I wanted to start out by doing an introduction to statistics. And I do this in probably a little bit different way than you might have experienced if you took a introductory statistics course. And I do this because I find that I think there's some confusion when it comes to doing statistics and applying it to real world data. So let me get my screen going here. There we go. So if I think everyone's on mute, and I believe we're supposed to send questions to the chat, not to the Q&A. The session is being recorded, so if you want to listen to it later, you can. And also after the session, I believe Georgetown sends out the slides. So you'll have both. If you need to contact me or have any questions, my email is the MedStar one at the bottom. Okay, so what I want to talk about today is primarily what statistical significance means. And when you calculate a p-value, what does that mean? And I started out with saying that there's a p-value crisis, and I'll try and explain what I mean by that. One of the things that I observed over the years in doing statistics in a medical research situation is that there is a fairly pervasive misuse of p-values. And I want to spend a little bit of time talking about alternative to p-values, and then make a couple of comments on how we might better present methods and results, statistical methods primarily in journal articles. So the p-value crisis I referred to was brought to the attention of statisticians, and our primary professional organization is the American Statistical Association. And so there was a question about why in introductory statistics courses in colleges in grad schools, why do we teach that p should equal 0.05? And the answer was that, well, that's what the scientific community and journal editors use. And then they sort of kind of going in a circle here. Why do so many people still use p equals 0.05? And because that's what they were taught in college. But anyway, this concern about p-values, and particularly the use of p being less than or equal to 0.05 as indicating statistical significance, was dealt with by the ASA board, and they came up with some recommendations, and I want to talk about those for a little bit. So the I guess before they met, they looked at some of the comments that were made about statistics by different individuals, whether they were scientists or not. Some of the more interesting ones, or the most interesting one, I thought, was the last one mentioned, the article that appeared in Nature, and I have a reference for that at the end. So if you can get a hold of that, it would be worth reading. So interestingly, in actually more recent times, some editors of journals have decided to ban p-values altogether. The idea of testing hypotheses. And I think that some people really argued, well, no, I don't think we should do that. But I think there's sort of a confusion about what statistical significance means and what a p-value means. So that's what I'd like to really focus on today. And the idea of p-values goes back 100 years now by the work of R.A. Fisher and Jerzy Neyman. And in the Nature article, Yuso says that the p-value was never meant to be used the way that it's used today. And then there are some who are calling for they actually entitled their article Abandoned Statistical Significance. That's not happened, and I don't think it will happen. But anyway, I sort of hope to clear up some of the confusion about what we do when we do significance testing and what that means. And as I mentioned, this goes back 100 years now in the 1920s, when R.A. Fisher, a really famous statistician, was developing some statistical analysis methods. And he actually did research in agriculture. And so he had these plots of different crops and so on, and would experiment about growing conditions and fertilizers and stuff. And so he was actually the developer of the analysis of variance method. And so when he was analyzing his results, an associate asked him, well, how do you decide if your hypothesis can be rejected? What's the smallest probability that you would accept it from your statistical test? And he said, well, probably 0.05. And or in other words, that he might make a wrong decision, statistically speaking, 5% of the time. And Neyman, in his development of null hypothesis testing and talking about the alpha error rate, never mentioned, using 0.05 as sort of a cutoff of being significant or not significant. So the American Statistical Association then came out with this conclusion that we should stop using the term statistically significant, nor should variance such as significantly different or non-significant be continued to be used. This was published in the American Statistician back in 2019. So again, if you're interested in reading their thinking about this, it's kind of interesting. My perception of statistical testing in medical research is that there's a fair amount of misuse of p-values. And one is that it seems like in a lot of articles, statistical significance, that is whether a finding or result when you get a p-value that's less than 0.05, that's kind of become the primary or even the only criteria for meaningful or important results, which we'll see is not necessarily the case. And then another, I think, really big misuse of p-values in the literature is what we call multiplicity or multiple testing. And we'll talk about that also in a little bit of detail. So I want to start out actually by sort of illustrating what we do when we do research, whether you randomize subjects or patients to a particular treatment or intervention, or whether it's just an observational study. But the basic idea of research is that you assume that there's a population that, as we use the term population, at least from a statistical standpoint, we mean everyone in the universe of interest. So if your interest is in all say males over the age of 75 with prostate cancer, and you want to look at that as your population and wanted to do research on that population, what you do then is you draw a sample or a subset of the population of interest. And as I mentioned, this can be random, or maybe it's not random. But anyway, the basic idea is that you have just part of the entire population on which to do your research. And so the question is then, well, is your sample representative of the population? And so this is where statistical testing comes in. The statistics is done on the research sample, and we're going to, or at least implicitly, make the assumption that the sample is representative of the population, and our statistical test is going to tell us whether there's a high probability or not so high a probability that our research sample is representative of the population. And so here's the basic idea of doing research, and then of the theoretical ideas behind hypothesis testing or significance testing. And so, as I mentioned, you get one shot at drawing a sample from your population. But theoretically, we could draw many samples, many hypothetical samples from our population. And so this is the idea behind random sampling, that each sample, and let's say we want to estimate the mean of our population from our research sample. Well, from the classical or frequentist point of view, there is a population mean here. Now, we'll never know exactly what that population means is, but by drawing a random sample, we want to estimate what that population mean is. If we were able to draw many, many random samples from our population, or non-random samples, we could see then that we would get some variability in the estimate of the population mean. And so the basic idea here is that there's a sample mean for each of these samples, which is likely not all the same. But if we were to draw enough random samples with the size of our research sample, then the mean of our sample means will equal the population mean. So even though we can't draw many or an infinite number of random samples from our population, mainly because we can't afford it or don't have the time to do it, but we're then placing our estimate on the research sample, or making our estimate of the population mean based on our research sample. And so I'd like to illustrate this with actual numbers. So let's say this is my population of blood pressures. And it turns out the mean of all these numbers here is 76. So we have a mean blood pressure of 76. And so our idea is that if we were to do research, we would draw one sample out of this population. But let's say that we can theoretically draw many samples, and so maybe we'll, randomly pick different samples of size 5. In other words, each of our sample has an N of 5. And so then for each of these samples that we randomly draw from our population, we can calculate the mean. And so I have a few here that I've drawn randomly of individual values in N's of 5, and calculated the mean of each of the samples. And so you can see that there's some variability here, that we have one sample here had a mean of only 67, another sample had a mean as high as 84. So the question is, we don't know which of these is our true population mean, and so we, in our sample, we are going to use our sample to estimate the population mean. And you can see that in about the middle of our different samples here, the means are pretty close to 76, which we saw was our population mean. Well, if we were to do this an infinite number of times, then we would get a really good estimate of the true population mean. And this set of means over here from different samples we call a sampling distribution. This is not a distribution of data. If we look at the distribution of data, we're looking at the distribution of the individual values here. But a sampling distribution is a distribution of statistics, mean being one, a proportion would be another example. And in our sampling distribution, if we were to do this over and over again, we would, of course, have variability, as we saw. And so there's two different measures of variability that I want to define here so that we're clear what they mean. When we hear the term standard deviation, we're talking about the variability of a distribution of data or distribution of individual values. The term standard error, however, refers to variability of a distribution of a statistic. And so, for example, the standard error of mean is just the standard deviation divided by the square root of the sample size. So it's important to know the difference between the two, but primarily just remember that when we talk about a sampling distribution, or when we talk about the standard error, we're talking about a distribution of statistics. Okay, so let me further illustrate this by taking some of the sample that from our population of blood pressure values, and we're going to calculate the mean of each one, and then we're going to calculate a confidence interval around this mean. And I'll talk about how we do this in a minute, but we calculate the standard error of the mean, and then so we find the standard deviation of our sample divided by, in this case, the square root of 5, and we come up with the standard error of the mean, which, remember now, is an estimate of the variability in our sampling distribution. So what we can do then is we can calculate confidence intervals about the mean. And so if we do a 95% confidence interval about the mean, then that's plus or minus 2 standard errors, because so about 95% of the area under a normal curve is about 2 standard deviations. So then from that, we can then calculate a lower bound and an upper bound for our confidence interval. So our lower bound is going to be 80 minus 2 times 3, or approximately 2 times 3. And our upper bound is going to be 89. 80 plus 2 times 3. I rounded here, of course. And so then in the right hand side here, I've illustrated this by drawing a graph or a picture of our confidence intervals in the relationship to the population mean, which you remember is 76. So here is our population mean of 76, and here is the confidence interval about that mean. So what we talk about then, when we talk about a 95% confidence interval, is that over repeated sampling, 95% of the time, the true population mean is going to fall in this confidence interval, is going to be included in this confidence interval. But of course, that means that on an average, that 5% of the time, the confidence interval will not include the population mean. And so you can see that happened a couple of times here. And so this means that we don't have a very good estimate of our population mean. Now, the question is, though, is how wide is this confidence interval? And so we can see that we can change that. If you remember, the formula for the standard error is the standard deviation divided by the square root of the sample size. So if we increased our sample size to 10, then our standard error of the mean would be smaller. So a really important principle here is that the larger the sample size, the better your estimate of your population parameters or your population statistics. And so in our classical view here, what we, when we talk about sampling variability, we're assuming the population mean is fixed, but it's the 95% confidence intervals that can vary. Okay, we can then carry this over to hypothesis testing, where we say want to compare, in this case, we'll compare the blood pressure means of 2 groups, treatment, some treatment that's been given to lower blood pressure, and a control which doesn't get the treatment. And so what we want to do then is compare the means of these 2 groups. And we want to ask did the treatment lower the blood pressure? Well, if you just look at the values of the means, you say, well, yeah, it lowered it by 5, millimeters of mercury. And so that might be, one answer that we could give, but as you look at it from a statistical point of view, remember that these are random samples from a population. And so there's variability about these means. And so when we test our hypothesis, what we are asking, is this difference a true difference, or is it due just to random sampling variability? And so when we do statistical hypothesis testing, we make a statement of 2 different hypotheses, the null hypothesis and the alternative hypothesis. And so obviously it's the alternative hypothesis that we're interested in proving, although we don't actually prove anything. But our null hypothesis then is that there's no difference between the means of the treatment and control group. In other words, this difference of 5 here occurred just because of random sampling variability. And so when we do our statistical analysis here, we're going to assume that the new null hypothesis is true. And then based on our statistical test, we will either reject the null hypothesis or we will fail to reject the null hypothesis. And so here's how we do that. We perform our statistical test. In other words, we compare the 2 means, and the decision that we make is really bivariate. That is, if our alpha error rate, the p-value, is small enough, or it's smaller than what we set it at, then we say it is significant or statistically significant. If our p-value is greater than our set rate, say 0.05, then it's not significant. And so you can see that when we make statistical decisions, we have actually two kinds of errors that we can make. And they're referred to as the alpha error and the beta error. And the alpha error is the willingness to make a wrong decision. That is, we reject the null hypothesis when in fact, the null hypothesis is true. In other words, based on our statistical test, we're going to say that there is a difference in the population. But it turns out, if we were able to look at the population, that that's not true. That there is no difference. The beta error is also another wrong decision that we can possibly make, and this is failing to reject the null hypothesis when in fact it is false. That is, based on our statistical analysis, we fail to reject the null hypothesis, but in the population, a true difference does exist. You kind of think of the alpha error as a false positive, if you're thinking that, and if you think in terms of tests for a disease, that the test can turn out positive, but they really don't have the disease, or the test can turn out negative, but they really do have the disease. So you can, if you think of in those terms, then the alpha and beta errors correspond to that kind of reasoning. When we make statistical decisions, it's important to understand that both alpha and beta are arbitrary. The p-value less than 0.05 has become kind of a tradition, really an entrenched tradition. And so I think virtually every study that you see that's published will have 0.05 as what they set the alpha error rate at. In other words, what they're saying is they're willing to be wrong 5% of the time if we were able to do this over and over again, the study over and over again. But if we say, for example, if we set our p-value at 0.01, at less than 0.01, then if we get a p-value of 0.05, then we'd have to say that it's not statistically significant. And so we would fail to reject the null hypothesis. And if we use a p-value less than 0.01 to reject the null hypothesis, we would be wrong on average, one time out of every 100 random samples. So this is one of the main points that I want to make is that the alpha and beta rates are arbitrary, particularly the alpha error rate. That the 0.05 is not a magical number, although it's kind of become a magical number in medical research. So a p-value then is the preset level. That is, we have to decide what the p-value or the alpha error rate is going to be for rejecting the null hypothesis before we do the study. We can't do it after the study. P-values are not the probability that the null hypothesis is false, and it's not the probability that the alternative hypothesis is true. And also, it's important to realize that it's not necessarily an index of importance or meaningfulness. And you often see the term highly significant, like, so you get a p-value that's, point, or has one with, 5 zeros in front of it or 10 zeros in front of it. And so people say, well, that's highly significant. Well, that's not exactly correct. When we talk about highly significant, that's making a value judgment. Because once we set our alpha level, then significance is or it isn't. What is typically meant when people talk about something being highly significant is that the p-value is really small. And so what is really meant by that is that there's a very small probability that the difference you found or the statistic that you found could have occurred just by chance or random sampling variability. And then another term that you often see in the literature is a trend towards significance. So they get a p-value of 0.06 instead of 0.05. Well, again, that's not really correct because, as we mentioned, when you make a decision about whether something is significant, statistically significant or not, it either is or it isn't. So if you've set your alpha error rate at 0.05 or 5%, and it turns out you get a p-value of 0.06 in your study, then it's not significant. But people like to think because it's really close, then it's like a trend, towards significance. But of course, the question is, would it matter if you had set it at 0.05 or you set it at 0.06? So we've mentioned this before about interpreting a p-value. So if our p-value is less than 0.05 or our whatever we set it at, 0.01 or 0.001 or whatever, then we reject the null hypothesis, having assumed it was true, and we conclude that the observed sampling statistics, whether it's a t-statistic or chi-square, was unlikely to have occurred by random sampling variability or chance. And so it's stated in terms of a probability, not an absolute yes or no. So if we have a p-value that's been set at 0.05 and we get a p-value that's equal to 0.05 or less, then what we mean by that is on average or over repeated sampling, we'd be wrong. We'd be making a wrong decision 5 out of every 100 times. The other important thing that I want to point out here is if our p-value is greater than our our preset alpha error level, say it's greater than 0.05, then we fail to reject the null hypothesis. And often you see when people get this, they say, well, there is no difference between, say, the 2 groups or 3 groups or however many groups we're comparing. Well, that's not a conclusion you can make, that there's no difference. The best you can say is that we found no evidence for a difference. Because if you don't find a difference, then the interpretation is that you probably didn't have large enough sample size to detect that difference that you actually found. So it's, even though that's commonly used, that there is no difference, technically you can't say that. The best you can say is that we found no evidence for a difference. And so if we, as I mentioned, if we fail to reject the null hypothesis, it might mean we didn't have enough statistical power to detect the difference that actually exists in the population. Or just put another way, we didn't have sufficient sample size, or you'll see the term used, we were underpowered. Sometimes, though, we reject the null hypothesis with small sample sizes. But the problem here is the results could very well be spurious. That is, if you have a small sample size, you're really not powered to do inferential statistics or to test or do hypothesis testing. And the reason, if you think about that, if you have a small sample, say you have a sample size of 10 in each group, or a total of 20, and you find statistically significant results. Well, if you got more observations and you say increased your sample size, then it's possible that you could not find statistical significance. So beware of p-values when the sample size is small. On the other hand, if you have a very large sample size, then it's quite easy to find statistical significance or reject the null hypothesis. But in this case, it's very likely that the results may not be really important, or as we say, clinically significant. So the biggest problem for null hypothesis testing is really our sample size. And so one of the sessions we'll have later on is how do we figure out the sample size? How, in other words, how many subjects or how many patients do we need to find the difference that we think is important. So what I like to focus on now is how p-values are misused in the medical research literature. And so I've taken this out of a study that was done a few years ago. And so this is their statistical methods. Continuous variables were analyzed by unpaired t-test or Mann-Whitney u-test. That's a test when the distribution is not normal, or the data is not normally distributed. Categorical variables were analyzed by chi-square or Fisher's exact test, and then they make the statement a p-value of 0.05 was considered significant. And that's a very common sentence that you see in statistical methods. Not that it's unimportant, but it implies some things that are not necessarily good to imply. And I'll have an example of that from the study that was looking at blood pressure in patients with shock after an acute MI and cardiac arrest. And so I don't want to go into too much of the details. You can, read this if you are so inclined. But their primary endpoint here was the area under the curve of two different groups. And so they randomized patients to a higher MAP or target that had 58 patients in them, and then a higher that had 86 patients, I believe, in them. And so what they wanted to do was to look at the area under the curve is their primary hypothesis. And so in the presentation of their results, I want to go over those in a little bit of detail here to show you what they did. So here's their table 1, which is typical of the tables you see of demographics and medical history. And they do two different ones here. It's how they define the ones on the right here are the primary interest, their categories of MAP, mean arterial pressure. And so they have age and distribution of sex and medical history. But you see that what they did for each of these, they have a p-value out here. So that means that what they did was to do hypothesis testing for each of these variables. Now, the problem is that these variables are not involved in their main hypothesis, but they did hypothesis testing for each of these. And so you can see that what we have here is the problem of multiplicity or multiple hypothesis testing. And when you do that, what you do is you increase the alpha error rate, or we say you inflate the alpha error rate. So if one of these happened to be 0.05, you couldn't really say that that was statistically significant, even though he said a p-value less than 0.05 was significant. Now, in a randomized study, you really shouldn't, people do this, but you should find that if they've been properly randomized, the values should be pretty much equal between the two groups, whether it's a mean or a proportion, whatever. You can see here, though, that, for example, like on medical history of previous AMI, so they have 9% in one group and 20% in the other group. Well, that's not statistically significant, but that's kind of a big difference there. So that might be a problem in our conclusions. Anyway, they continue table 1 with more baseline characteristics, and you can see that they've continued to do hypothesis testing for each of these variables. So you're really have a problem with multiplicity here. And then they also do the same thing with angiographic findings and calculate a p-value for those as well. And then we finally come to table 3, where this is where they do a test for their primary endpoint, the area under the curve. And so this is the p-value that would be most interested in. They find it's 0.04, so they conclude that there's a statistically significant difference. But they also have several secondary endpoints here that are not significant, but they've added to the number of statistical tests they've done. So if we were to, and I don't remember how many it is, but if we were to look at all the different hypotheses they tested, then we would need to make some correction for multiple testing. And so for certain, if we did that, this 0.04 would not be statistically significant, because our p-value would have to be much smaller to conclude that there was a statistically significant difference between any of these variables. So even though they, in their article, conclude that there was a significant effect from the treatment, that we can't really conclude that because of the multiple testing. So when you say in your statistical methods section that like a two-sided p-value less than 0.05 was considered significant, you need to kind of think about that. Are you applying this to all the different p-values you're going to calculate? Are you talking about your primary hypothesis? What exactly do you mean by this? So, and our conclusion is that if you do multiple hypothesis testing, then you're going to have to make some sort of adjustment for the inflation of the type 1 error rate, or you're going to have to generally declare something statistically significant at a p-value that's probably smaller, and sometimes much smaller than what you said it was. So, and the most common way of doing this is with what we call a Bonferroni correction, where we take our alpha error rate, our 0.05 in this case, and we divide it by the number of tests, the number of hypotheses we're going to test. So if we were going to do 5 different tests, we divide 0.05 by 5, we get 0.01. So that means that any of the 5 tests that you do have to have a p-value of 0.01 or less to be declared statistically significant. The problem you can see with that is if you have a lot of hypotheses you want to test, dividing 0.05 by 20 or 30 or 50, however many you want to test, can get pretty small. The p-value can get pretty small. So one way to get around this solution to multiplicity is don't list the p-values in table 1, and that's actually the position that the New England Journal of Medicine takes now, that in table 1 you're not supposed to list p-values. Another thing you can do is calculate standardized differences, which is essentially an effect size, which doesn't depend on sample size, and so you're not really doing hypothesis testing. I have a few slides here on what standardized differences are. I won't go over those in detail. You can look at those yourself, because I'm kind of running short of time here, but basically standardized differences correspond to a percent of non-overlap in the respective distributions of sample statistics. So you can see in A, we have a lot of overlap, and in plot B or figure B, we have quite a bit of non-overlap. So these are the formulas for calculating standardized difference of means and standardized difference of proportions. And in the table here that we looked at before, instead of doing p-values, it might be more interesting to do standardized differences, because in a lot of ways you can get actually more information from a standardized difference than you can in just looking at p-values. And you can see here that we have a couple of standardized differences that are fairly large, like in the order of 0.3 for two of our variables here that were not statistically significant. And then we can translate a standardized difference into a percent of non-overlap. So you can see here that the bigger the standardized difference, the further apart your distributions are. Okay, so I have some slides here on the statistical methods that appear in the article, and how I might rewrite that to be more in line with what the American Statistical Association is saying. And so instead of just saying our p-value was less than 0.05, we could say something like the alpha error rate for assessment of random sampling variability with respect to the difference was set at 0.05 or 5%. So it's just sort of recognizing what a p-value means, that we're talking about whether we can reject the null hypothesis based on chance or random sampling variability or not. And then in the results, they said don't use, the essay said not to use the term significant or statistical significance. And so this is just another way that you might say that without using the term statistical significance. But like I say, this is hardly, I think, ever done even now in most journal articles. And so let me conclude by just saying that just to remember primarily a p-value is just really one check on a study validity, and the check that you're checking, the box that you're checking on a say, is that were your results likely due to chance, or can we is there a high probability that we can rule out chance as a explanation for your results? One thing that they do say that the ASA says, don't use the term statistically significant or non-significant. I'm not so sure I would go that far. What I don't typically encourage people to say, or tell them, don't say this, don't say highly statistically significant, or use a trend in significance. And so when you make your conclusions in your study, make it, think about what your study means, what the results mean. Don't just say, our results are, there was a difference in our p-value was, less than 0.05 or whatever it might be. And I wanted to conclude by saying that in the 2 or 3 years that the ASA has had their position out on use of p-values and significant statistical significance testing, from what I've seen, it's had virtually no impact on medical research publications, and people still do that. But if you're aware of what a p-value is, then you can make an intelligent decision about the results and the conclusions that they make in any particular study. So I will stop there. I have some references here, which, as I say, these slides will be made available to you. And then I want to thank you for your time and attention. We do have just a few minutes here. I'll stop sharing. And if you have any questions, you can put them in the chat. And if we run out of time here and you have to leave, then you can email me the questions. Or I believe also I have any questions are recorded here, so I can go back through the recording. Okay, great. If there's no questions, then either I made it really clear or really foggy, or you really knew this stuff anyway. So I want to again thank you, and I'll stay on for a few minutes if someone does have questions. Otherwise, we will see you next month.